Okay, good afternoon, everyone, and thanks for attending our session. We're going to talk about routing every Android from extension to exploitation, which basically will be focusing on the security of the Android kernel in our session. And first, some brief introduction. My name is James. This is Shen, and aka Redmi. We both work for the Lab of Tencent. And we are really into the Android kernel security because we focusing on routing all kinds of Android devices. And our lab has been working on Android security, Android kernel security for more than 2 years. And during that course, we are quite proud that we contribute to multiple non-malicious routing solutions, which are quite welcomed by the communities, including the ping-pong root, which was released last year to be one of the first root utility released for the Galaxy S6. And also the CVE 2015-8805, which was released this year, and actually pushed Google to release its first security advisory of Android during the history. So these are two major generic routing tools we worked on, and also we released some multiple, quite some device-specific routes, which will also be discussed in today's session. Okay, so here's the agenda of our session. And today we are going to discuss a very interesting attack surface of the Android kernel, which is named wireless extension. So this actually exists in almost every Android device because most of the devices comes with a Wi-Fi chipset. So during the session, we are going to give you a generic overview of how this interface looks like and what are its potential weakness spot and how we actually discover vulnerability inside it. And following that, most of the time we'll be spending on 3 different cases. They are actually affecting not just the different SOC, but also comes in with different types of vulnerabilities. And last but not least, we'll also mention Google's latest mitigation, which helps reduce and mitigate the attacks from this attack surface. Okay, so first thing first, let's get into the overview section. So what is the Wi-Fi, or we call wireless extension of Android? We all know that beneath the Android, beneath all the graphic stuff, we still have a Linux kernel there. And for Linux kernel, there are a lot of contributions from different communities, and one of them is actually a wireless extension, which was designed by Gene. He is a HP lab researcher, I think, whose main concern of research is communication and network protocols and all this kind of stuff. So he was quite concerned by the varieties of different wireless drivers in the early times, so back in 1997. So he would like to design a wireless, a standard and uniform way that user can manipulate any wireless networking device. That's a setting some standard for the wireless devices drivers for the Linux kernel. So eventually, he designed this wireless extension API, which was implemented in almost all major wireless solution vendors, by almost all the major wireless solution vendors. It will be replaced by CFG 802.11, which should be a little bit newer, but also still supplies with backward compatibility. So if there's some issue in the implementation of the wireless extension, it is still potentially can be attacked even the device comes with the latter wireless extension standard. And also it doesn't mean that CFG 802.11 is more secure, because we are also seeing vulnerabilities discovered in the implementation of this API. Okay. So let's look into the interface itself. Let's look into the wireless extension API. And it actually comes in 2 major interfaces. One of the interfaces actually is implemented as a procfs node, which just provides some status which you can query. Basically just read that file. It's under proc, net, and wireless. So just get the file and you'll see some statistic data of different wireless interfaces, which does not provide too many features there. So this does not likely to be some kind of major attack surface of the wireless extension. The other one is almost everyone's favorite, especially for Linux kernel researchers, security researchers, which is the I/O control interface. So the I/O control interface will provide a group of commands and different functionalities, which allows you to set or query for parameters for that device. Or you may also issue commands for the device, for example, enable certain wireless features or turn it off. So it provides a very feature-rich interface, which can be a potential attack surface as well. And let's take a look at how this I/O control interface was implemented. So we all know that I/O control interfaces come with command, and it actually reserves a certain command range from AB00 to ABFF. There are actually 256 commands available in this range, and they are actually just reserved just for the wireless extension commands. So you can see actually there could be many features implemented in this interface. And actually it sets some kind of quite interesting rule for get and set commands. So if that command comes with an odd number, then it will be a get operation. Or otherwise, it will be a set operation, just as defined in these two macros. Well, this is quite clear, but well, this also caused some kind of problems. So we'll see this actually caused some troubles later in the case studies. So besides this, there is merely any kind of access control implemented on these I/O control commands, which also makes it a great attack interface. And later there will be a more detailed research. And one more important thing is that according to the document of the Wi-Fi wireless extension, which is in the comment of this header file, it says that this is not magic. So almost every feature needs to be implemented by the SoC vendors for them. There's no generic uniform implementation in Linux kernel. Everything is done by the stock vendor. So which means that there are more likely to be some issues in the code rather than just mainline Linux code. So this is a generic code path. If you issue a I/O control command on a socket, which is open on a wireless device, what will happen? And we're pointing this out because this also describes the access control, which is enforced by the Linux kernel when you actually issue this I/O control command. So starting from this I/O control, we know that there is LSM, the Linux security module there, which may actually put some enforcement on the operations which user-space application can do. And in our case, for Android, it's SELinux. So the SELinux policy is going to be enforced on our control command. And if our control is not allowed for this process, it will be actually denied. And going all the way down there, there's almost any kind of access control until before actually calling to a driver, I mean the vendor specific code, there's going to be a it will going to check the actual I/O control command and see whether this is actually a set or get. If it is set, which means it is actually write operation, and the net admin, the capability of net administration is going to be enforced. And there will be, so normal users without this capability will not be able to operate on that socket with that specific I/O control command. So as you can see from this diagram, basically there's almost no other access control is applied on this. So we can see that this is actually a great attack surface to play with. So we'll be looking into three major wireless Wi-Fi device vendors, which the first one is Broadcom, the second one is Qualcomm, the third one is MediaTek. These also covers most of the Wi-Fi chips which are being used in the Android devices nowadays on the market. So if you can find vulnerabilities in all of them, then basically you can root off the devices. And our first case will be a vulnerability, a stack overflow vulnerability in Qualcomm Wi-Fi extension. Okay, so this vulnerability was reported by an anonymous source, which in the bulletin it was translated as 人假路, which is actually 路人甲, means anonymous in Chinese. Pretty interesting. Assigned with a CVE number 2015 0570. And in the advisory released by Qualcomm, so it is also notable that it's fixed something which is caused by the odd I/O control number rules we mentioned earlier, which it adds some specific controls and some specific checks in the I/O control handlers themselves right here. So actually we can see that this rule, this odd number rule, is not being well respected or be well known by the vendors. So when implementing those IO control commands, they are not actually strictly putting all the set commands into even numbers and all the get set commands into odd numbers and get commands into even numbers. So this actually caused some kind of privilege leak in those devices. So they have to enforce certain access control in the code itself instead of relying on the original access control designed by the wireless extension. So, and besides that, more importantly, is a stack overflow vulnerability fixed in this advisory. But there's one problem here. So we all know that stack protector has been widely enforced in most of Android kernels, I mean, in the recent 2 or 3 years. So why that a stack overflow vulnerability can still survive in a wireless extension driver? Because there should be a stack canary there. But the fact is that the stack protector compiler extension is not as good as we thought. It actually misses a lot of functions which actually demand a certain level of protection. According to some statistic by, I think, by Google, it only covers like 2% of all the functions. But among them, many of them actually demands protection because they have certain buffers on the stack which user may write into. And in this case, actually, stack protector strong was being recommended by Qualcomm and Google, both of them, after this vulnerability was addressed, that it should be used by the kernel, everyone to compile the kernel instead of the stack protector, because after it addresses some issues in the original stack protector. And also this stack protector strong function requires GCC 4.9 or later version, which is a certain recent version of the GCC. So the vulnerability itself sits in the function of WLAN HTTP set filter, and we can see on the right side that this data structure actually contains certain char arrays. Let me highlight that. So it contains 2 arrays with a size of 8 bytes. And if you check the stack protector code, well, you'll be aware that actually 8 bytes is the limit. I mean, any buffer equal to or bigger than 8 bytes are going to be protected by the stack protector. But the problem here is that this structure is actually nested in another structure as an array member. And this actually triggered a bug in the GCC, which this original stack protector does not check nested structures in an array. So all these buffers are being overlooked. So that's why the stack canary does not apply and eventually lead to the vulnerability we're talking about in this session. And here are just the code which causes the stack overflow. It's very straightforward, lack of check on the length when the arguments are being passed to the kernel from the user space. So on the other word, the user actually has direct control over both the length and the content, so a perfect stack overflow vulnerability. And also the trick is very same. We just overflow the stack and override the LR and try to get the PC control over the whole process. But just one thing to mention here is that actually on ARM64 devices, it's quite hard to exploit because you are controlling the X29, X19 register instead of the conventional ones, usually X0, X1, X2. Will be easier to make a JOP chain to actually achieve the target of root. So we actually used a modified version, an earlier version of Roper. I made some modification to that, and to find a pivot gadget first to transfer the X19 and X29 control to X0 and X1. And then there will be 2 conventional gadget chain, which then we can use to achieve the goal of leaking the stack pointer and eventually override a DDI limit, so we can gain kernel read and write after that. Okay, so this is the first case, and we can see that actually a stack overflow vulnerability can still exist in modern devices, even with the compiler extension of stack protection. And lately, Redmi will introduce 2 other more interesting cases which affecting 2 different wireless vendors. And also, he will conclude with the Google's latest mitigation of this issue. Okay.
Thank you. Here comes the second case. The discovery of that Qualcomm vulnerability put our attention focused on WXT, and so I continued the work and found some other vulnerabilities on MediaTek WXT and the Broadcom WXT. And this bug is a data section overflow, and it's obviously exportable. So I just finished exporting the exploit in 2 days without any hard-coded symbol address, and at that time we didn't report it to Google yet. But taking into account that it's very easy to find this vulnerability by code auditing, so I'm not very surprised that another researcher from Google Project Zero also reported to Google at December 2015. So the CVE number of the second case is CVE 2016 and 0820, and it affected all MediaTek devices. Actually, it's a very classic copy from user issue, and the WXT handler copied the input buffer from the user space to the data section without verifying that the size of input buffer is less than the size of output buffer, so leading to a data section overflow. The destination address is AUC OID buff, and I'm going to highlight it. And it is 4,096 bytes in data section, and the vulnerable code has been shown on the slide, so you can see that the data length is provided by user and can be any value. So in this way, we got a chance to overwrite other variables just behind the AUC OID buff and in the data section. So how to exploit it? A classical idea to achieve kernel code execution is overwriting a global function pointer located behind the AUC OID buff. And so I'm going to highlight, and I'm going to overwrite this function pointer. And in this case, I'm going to try to overwrite the pfwlen remove. But to avoid a kernel crash, I better not craft other unrelated global variables in gray. So I better know the data of these unrelated variables, and I also have to know the relative offset to the AUC OID buff. So I need to know the offset here. So another vulnerability, which is leaking the value of these variables, is necessary. So fortunately, another command completes this task perfectly. There is no boundary check when called copy to user. So we just get the value of these variables behind the GUC. Oh, I'm going to highlight. It's here. The GUC buff debug code. This variable is just behind the this variable is just behind the AUC OID buff. So in this way, we can ask the kernel to copy these variables to the user space. So so all these variables can be leaked. So my export will not crash kernel anymore. So now it's time to allocate some pages in user space and copy the shellcode to these pages, and then get the direct mapped address of these pages in kernel. It's also known as the return to direct mapped memory, which is presented by Vasilios Kamerlis at Black Hat Europe 2 years ago. I really admire his work, and please also note that these pages are executable in kernel space on MediaTek devices, so that I can execute the kernel code without any JOP or RLP guidance or hard-coded kernel symbol address. They just execute the shellcode in the kernel. Then I will, since I have already overwrite the pfwlen remove with the kernel address of the shellcode, and so finally I will call a Java API which is set Wi-Fi enabled, so that in this way system process which is mtkWMTD, which is provided by the MTK vendor, will call the pfwlen remove to execute shellcode in kernel space. So finally, we will gain root privilege and recover. After that, we will recover every modified global variables. So that's the second case. So here comes the final case, and I think the previous two cases are kind of warming up because the third exploitation is much complicated than the previous two cases. So firstly, it is a user-free due to the race condition, and the naughty problem is the window is very small, so I need to refill the freed object in a very short time. This is the biggest challenge of this case. And I will also introduce two separated issues. The first one is a lack of privilege check while processing the WXTL control, so that any local application can call the WXTL control to the Broadcom driver and attack it. The second one is the use suffer free when called the WL Android Wi-Fi off concurrently. So this vulnerability will affect all premium and Android phones like Samsung Galaxy series and Huawei Mate series, and also Google Nexus 6P and many other phones with a high price. And before I introduce how the vulnerability is going and how to exploit it, there is another interesting fact is that the second issue is discovered by running some test code while pressing the Wi-Fi button on and off repeatedly and crazily. And then the kernel crash and the crash is reproducible. So after analyzing the crash, I realized that I found the user perfect bug accidentally. So by analyzing the crash message from kernel, you can see that the name of process who triggered the crash is thread 128. It means that it's a bundle thread belong to the system server. The system server is a core process of Android running in user space, and it has several worker threads to handle the bundle IPC request from other applications. And by analyzing the core stack of the crash, you can see that it crashed while calling the WXTL control, and so this core stack belongs to the WXTL control handler. So after that, by reproducing and debugging the issue again, finally I realized that it's a use suffer free due to the race condition between attacker's L control request and the system server's L control request handled by the Broadcom WXT. So I just say that there will be two separated issues. The first issue is CVE 2016 and 2475. The WL Android privilege CMD is able to be called with insufficient privilege. It means that any local application can also call this function to change the status of Wi-Fi chipset directly. So in this image, you can see that the DHDL control will process this command, which is SIOCDV private +1. And but there is another permission check just behind it. It's over there, but it's too late. The let L control command has already been handled without any permission check, so that's why it is an issue. And so we just go into that WL Android priv command. In this function, a large number of commands will be progressed without any permission check, and the most attractive to me are the CMD start and the CMD stop, here and here. So because these commands will trigger the UEF bug, and after all threads, if two threads disabling the Wi-Fi concurrently is why the UEF happened. And okay, so here's come the second issue. It just has no CVE number and never appeared in Android security bulletin, but it's absolutely exportable. The patch is quite simple. It just removed one line code here. Oh, sorry. The slides crashed. Just wait a second. So let me jump to the slides I'm talking about. Perhaps I found another vulnerability accidentally. Oh, I think it's here. Okay. So the patch just removed this line, and it means that in case PCIe bus already done, it should not disable the IRQ calling anymore, because when the bus is done, lots of resources and objects has been freed, and the removed code will still reference these resources and objects, so it will trigger a use suffer free bug. But I found the bug accidentally, but how can I write a POC to trigger the UEF bug? So according to the analysis of kernel crash, I thought the flowchart of use suffer free should be like this. And if two threads called WL and join Wi-Fi off simultaneously, at first the bus state is up. So the first thread will go to the yellow branch and may free the SI info here. The SI, this function SI detach will free the SI info, and finally it will set the bus state to down. So after that, soon after that, the second thread will go to the green branch because the bus state has already been done here. So it will call this function, and finally it will call the SI core rex to trigger the use suffer free. But unfortunately, in fact, we can't do that, because if we want to call that function concurrently, we need to call the DHD IO control entry. But this function is locked. You can see a lock here, so we can't call it concurrently. So we need to find another solution, because finally we are going to call this function concurrently. Maybe you can find another way, not via the DHD IO control, but use another function to call it. So fortunately, the WL and join Wi-Fi off also can be called via the DHD stop. The DHD stop is here, and by calling the DV90L control with a command code which is SIOC SIF flags, but calling this function requires a cap net admin privilege, which we don't have, because we are local applications. Only root user has this privilege, but we can use another Java method to ask system server to do the favor. So if we call the Java method which is set Wi-Fi state, and the system server will help us to call this L control and in the bundle thread, and finally it will call the WL and join Wi-Fi off. So in this way we can call that function concurrently. So here is a real flowchart of the UEF. Attacker should create a thread to call the WL and join Wi-Fi off to free that object. So he will create a thread here, and finally it will call the SI detach to free the SI info object. After that, he will call a Java API from via the bundle APC. So the system server will help us to call the WL and join Wi-Fi off concurrently. So finally, it will trigger the use suffer free. So these pieces of code show that how we can control the code flow when use suffer free happened. If the refilled object meets several requirements, it will reach a macro here. But before that, you need to make sure that the bus core ref is not equal to the 2, 4, or 6, and the SOCI type must equal to the SOCI SB, and the bus type should not be either of them. These variables are all the members of the freed object SI info, so we can control that if we can refill the freed object. So finally, it will reach macro here, and you can see that SI is the freed object that you can control. So here is a function pointer, and here is the first argument. Both of them can be controlled by the attacker. So in this way, we can control the code flow and execute kernel code. So since it's a use suffer free due to risk condition, so we need to care about the window. You can see that the window is quite small. I have already added some print k logs in the kernel, so it can tell you when the object was freed and when it was reused. In fact, attacker only has 0.02 seconds to refill the object and execute code in kernel. So the object refueling is a big challenge. So let's talk about the racing and object refueling. If the racing failed, nothing will be happen except an error returned. That is okay. But if the racing succeeds but refueling failed, kernel will crash. So we have to find a way to spray the kernel heap efficiently and quickly. And also, in this case, we better fully control the data and the length of the refueled objects. So normally, I will use the send message to spray the kernel heap, and this time it's still working. Okay, so how to spray the kernel heap by send message? Firstly, I will create two processes as server and client the client should send bytes over the TCP connection and using the send message, but the server should not respond that. Just like the client, just like the message header, you can see that here. This is the message header, and in this structure, you need to let this function pointer message control point to the content you want to spray, and just as the server never responds to some message request from the client, the kernel buffer of the message control will be permanently stay in the kernel heap. So to spray the heap in the kernel, just create many pairs of server and client and do the above steps. In this way, it has a 90% success rate to refuel the field objects in the 0.02 seconds, and the data and the length of the sprayed object can be fully controlled. Unfortunately, the freed object, which is SELinux, is allocated in the kmalloc with a size 256. This approach will be not working if the object is larger. For example, the object is 512. It will be failed just because some message will allocate other same-sized objects as an interference with a spraying. So finally, with the approach we have talking about, finally we got a kernel code execution. But after that, you still have lots of work to do. Since the PXN restrictions, you need to build the GOP guardians to bypass the restriction and execute code in the kernel. After that, the first thing you need to do is manipulate the credential of your attacks. In other words, you need to change your UID to 0 and change your security ID to 1 or to the ID which belong to the init process. So in this way, you can bypass some SELinux policies. And you can also just directly disable the SELinux in the kernel. So in this way, you don't need to care about SELinux policy. But after that, you still need to bypass some vendor-specific mitigations. The most famous one is SamsungNox, and we have already disclosed how we bypass the SamsungNox on Galaxy S6. And after that, in not too distant future, we will also introduce how to bypass the bypass the SamsungNox in the Galaxy S7, but not this time because the vulnerability are still not be fixed, and maybe later. So after we found so many vulnerabilities and developed so many exploits about the WXT, Google also realized that the WXT is a big potential attack surface on Android. So a new mitigation has been applied since July's Android Security Bulletin this year. And the discovery of the CVE 2015 and 0570, which is the first case we just mentioned, put researchers' attention to the WXT, but the second case just drove Google to reduce the socket L control permissions filter. You can see that this is a patch for the mitigation, and this mitigation has the same bug ID with the second case. So I'm sure that just our second case study just drove Google to reduce the socket L control permission. So in the latest SELinux policy, now only a limited set of socket L controls can be accessed by unprivileged applications. And I'm not surprised that the private WXT L controls are disallowed right now. So if you want to call the private WXTL control on updated Nexus devices, I'm afraid that you will get an AVC deny error from the kernel and light just like this. So finally is a conclusion. So after we use 3 exploits mentioned above to root large number of devices with Qualcomm, MediaTek, and the Broadcom Wi-Fi chipset, I believe that the WXT private L control it was once an awesome attack surface on Android kernel, and the normal code in Linux kernel is really safe because it has been a long time and so many researchers are working on that, but the vendor code is still buggy. But Google really did a good job on surface reduction in this year because they did disallowing the WXTL control is just one of their contributions. They also do some other works to reduce the more and more attack surface on Linux kernel. So you can check his blogs, which the article is protecting Android with more Linux kernel defenses for more details. But in summary, for us, rooting Android is becoming more and more challenging. To root Android device again in the future, we can try to find some attack surface, little known just like WXT, or just discover another universal vulnerability in the generic syscall like CVE 2015 and 1805, which is an L vector overrun, because it's happened in a generic syscall, so it will affect all Android devices. And maybe some of you have already heard that the dirty call is really amazing and it's incredible for me. But for us, we are good at finding the memory corruption bugs, but not like the dirty call. But for Android devices, actually, if we want to disable the SELinux totally, and we still need an exploitation. But dirty call only can bypass the SELinux, but it cannot get the kernel memory overwriting. So I think it's not good for us to write a kernel exploit with the dirty call. So for us, we still need to find another kernel exploit in the future. And the final way, there's another way, which is compromising the privileged process first, and after that you can access some driver that you cannot before. So after that you can attacking the drivers which are only accessible to the privileged process. This is another option, but compromise user mode process on Android is pretty hard. I think it's just another hard work. So, okay, that's all for our presentations. Thank you for attending, and we really appreciate that. So, if you have questions, you can ask now. We are happy to answer it.
So, any questions?
A quick question about the heap spraying method. You said that you are putting the content to spray in message control, right?
Yeah, message control.
So as far as I know, isn't message control goes through a sanitation check when you send it via send a message for like file descriptors and any kind of this data?
No, we're talking about if any sanitizer can be implemented when actually the send message is issued by the user space applications.
Excuse me?
So you're talking that any sanitizer can be.
I mean that when you use message control for heap spraying, usually it goes through input type sanitation for file descriptors, because this is the field that usually is used to transfer file descriptors and spatial data for specific protocols. So as far as I know, and I might be wrong, it goes through a sanitation check, and therefore it does get allocated, but then it is immediately freed because the sanitation failed, unless your spraying data matches exactly the file descriptors array in the kernel, which is unlikely.
I think that the cases we are talking here is actually not just for the file descriptors, it's just some kind of generic message exchange mechanism inside Linux. I don't see any sanitizer in this mechanism yet. So basically, it's still a actually, the standard message is also used in our 1805, the CV 2015-1805, the vector overrun exploitation, to actually concat another piece of our vector array after the one which we are going to overrun into and have fully controlled data, so we can actually exploit the vulnerability. No problem.
Anyone else? Question? Thank you, gentlemen.
Okay. Thank you, guys.
Thank you.
Thank you.